Okay, so looking at power here, and the good news about power is that we don't have to do any calculating on a unit exam to do with power, which really isn't saving you a whole lot of grief because it's a pretty easy calculation. But for some reason, they've removed that from the program of studies. You just need to know what power is. All right, so if something is really powerful, what can it do? Okay, it can move things. What kinds of things? Heavy things, light things, all things. Okay, yeah, it can move things. But if I was comparing something very powerful to something less powerful, what's going to be the difference? Let's say I'm comparing them, but I'm using something they could both move. If we're deciding about a moving object, would move it faster or more quickly. Okay, power is not about how much work you can do. Power is how fast you can do the work. Okay, it's possible for a less powerful machine to do the same amount of work as a more powerful machine, provided you give it enough time. Okay, so power isn't about the amount of work, it's about how fast the work gets done. All right, so easy example would be like if you had an 800 watt hair dryer versus a 1500 watt air dryer. Which one is going to dry your hair faster? The 1500 watt hair dryer is going to dry it faster. It might cook it, but it's going to dry it faster, okay, because it's more powerful. Doesn't mean the 800 watt one won't dry your hair, but you got to have a half an hour to sit there blowing hot air on your hair, okay, in order for it to get the job done, okay, whereas the 1500 watt one will do it almost twice as fast. Okay, so power is only about how quickly the work gets done. In fact, it's the rate at which work gets done. All right. Now, as I've given away here, the units for power are watts. Okay. Most of the time, we associate the unit of watts with like light bulbs. Right. That's where we see it most often. Okay. Even as early as 10 years ago, we still had lots of light bulbs in houses that were incandescent. That's the kind that have the tungsten filament that glows white hot and makes the light for you. Okay, but we've gotten rid of those because they're not what? They're not efficient. Okay, they would use 60 watts of energy in order to do their job. That's 60 joules per second to power an incandescent 60 watt light bulb, 60 joules per second. So a watt is a joule per second. In other words, the rate at which work is being done. Okay, it's joules per second, it's how quickly I'm doing the work. Now, shortly after that, we developed those coil-shaped compact fluorescent light bulbs. Okay, you could replace a 60 watt incandescent bulb with a 13 watt compact fluorescent bulb, which everybody thought was wonderful until they realized there was mercury in the base of all of the compact fluorescent bulbs and they were an environmental catastrophe. So we quickly got rid of them and replaced them with LEDs. Now we all use LED bulbs. You can replace a 60 watt incandescent light bulb with a 4 watt LED. Okay, it puts out the same amount of light, but only uses 4 joules per second. 1/9. No, sorry, that's not right. I was thinking 36. Okay, significantly less, 1/6, okay, of the energy, okay, that would be involved, maybe even less than 1/6. Okay, we're looking at a lot, 1/15, okay, something like that, depending on which model you have, okay, of the electricity used, okay, by the traditional incandescent bulb. All right, the reason an incandescent bulb used so much electricity is it used heat to make light. Okay, those tungsten filaments were not good conductors. Electricity would really stall as it went through, and they would glow, and that's how they would make the light. Whereas an LED is a light-emitting diode, works a lot differently, okay, and does not emit much heat. Okay, if you were ever changing a light bulb, okay, like an LED bulb, it could have been on for hours. You can reach up and unscrew it, and you won't burn your fingers. You couldn't do that with an incandescent bulb. If it had been on for 15 seconds, you couldn't touch it. Okay, it would burn your fingers. All right. Everybody with me on that? There's also the nice thing about LED bulbs in that they don't explode. Okay, both compact fluorescents were really bad for that, but tungsten filament bulbs were also really bad for that. Okay, so there's lots of advantages, but the main one being they use less joules per second. Okay. Well, I don't know why the compact fluorescent ones would explode, but I had 2 that like were smoking on me in my house. Like my son came out, what's burning? I'm like, I don't smell anything. And then I walk underneath in his room, there's smoke coming out of the light. Okay, and it's one of those compact fluorescents burning. Yeah. Okay, so power relates to how quickly work can be done. Okay, not how much work is done. Obviously, if time is a factor, we want the more powerful machine because it's going to do more work, okay, in the same space of time. Okay, but if we're looking at efficiency, sometimes the less powerful machine is better. Oftentimes, they'll be more efficient. All right, comparison. These two cars, two 1996 Honda Civic hatchbacks. Okay, yeah, they're ancient, but hey, whatever. This one here you could buy from, the Honda dealership and go from 0 to 60 in 2 weeks. Okay. Got pretty decent fuel economy for a small car. Okay, or you could go fast and furious on it. Okay, throw a couple of turbos and air intake and a whole bunch of other fancy stuff onto it, and you'd be able to go from 0 to 60 in a lot less time. Okay, obviously the fast and furious, pimped out one over there is obviously more powerful. Okay, it can do the same job, that is carry the car from 0 to 60 miles an hour in a lot less time. All right, so if that's the only concern, then that car is better because it's more powerful. Is that always the only concern? No. Okay, if it's going to do that, is it likely to be as efficient? No, and it's probably going to use more energy in the process. Okay, so things to think about. Okay. Similar thing could be with things like lawnmowers. Okay, like people sometimes have an electric lawnmower. Okay, they're not usually as powerful. They're usually like 2 horsepower tops. Okay, whereas if you have a gas-powered lawnmower, you can get those up to 6 horsepower. Which one's going to mow your lawn faster? Yeah, the 6 horsepower one, because you're not going to have to go over it twice. Okay, whether it's 1 horsepower or 2 horsepower, you might have to cut it once and then go back over it to pick up all the clippings because it's not going to do it all. Okay, so a more powerful machine in that case does the job much faster. Okay, so these two machines. Okay, on the left we have a traditional water wheel. Okay, which is an ancient type of turbine. Okay, the water goes over it, it turns the crank. Okay, and if it's attached to a generator, could generate electricity. Okay, this is Grand Coulee Dam. Okay, it powers much of the Pacific Northwest. Okay, so that would be like Washington, Idaho, Oregon. Okay, they're essentially the same kind of machine, but one is more powerful. Grand Coulee Dam, obviously. Okay, is it possible for the water wheel to do as much work as the dam? Yes. If I run the dam for 1 second and the water wheel for 10,000 years, yeah. Okay, it could do just as much work as the dam. Not the best scenario. Okay, but again, its power is not about how much, it's about how fast the work gets done. Okay, that's really the thing you have to remember here, guys, is that power is just about how quickly the work gets done. All right, so looking at our units here, okay, so power is calculated by going work divided by time, okay, so that's going to be joules divided by seconds. That's where we get watts from. Okay, if we're saying something is measured in kilowatts, then we're talking about thousands of watts per second. Megawatts, millions of watts per second. Okay, and those would be the kind of power outputs we would see from power plants and things like that. Okay. Work and time are scalar quantities, so is power. Okay, power doesn't have a direction, it's just how quickly the work is getting done. Okay, so looking then at a formula here, not that you have to do any calculations, but important to see kind of the derivation here. Power is work divided by time. Okay, how do we calculate work? Force times distance. So we can go force times distance over time. What's distance over time? Velocity. So we could also write it as force times average velocity. Okay, if we're talking about an accelerating object, we could do that. We could calculate the average power by taking the average velocity, the one in the middle. Okay, we could also have change in energy, okay, over time as another one, which would involve, the final minus initial and all of that stuff over time. Any one of those things can calculate power. There's lots of different ways to do it. I think that's more why they eliminated it, because there was just way too many ways to do it, okay, as opposed to many of the other things that we do. Okay, so that's what we just did here, was looking at those other derivations there. All right, now, oftentimes people ask me, okay, well, the metric units for power are watts, but we talk about horsepower all the time, okay? Well, why did we originally use horsepower? Well, why horsepower was the original unit for power. Why would that have been a logical unit to use? Well, actually, we didn't even use the unit horsepower until some invention was developed. Yeah, the internal combustion engine, car, the tractor. Okay, we only used horsepower once we started marketing those two things, because what were they designed to replace? Horses. People needed to know, how many horses will this machine replace? Okay, that's what they needed to know. All right, so that's where the units of horsepower came from. Now, in terms of how many watts in a horsepower, all right, here's how you figure that out. You attach a horse over a pulley to a bunch of weight. And as long as the horse can walk at 1 meter per second, okay, they're going to exert a force on this object, okay, of equal to its weight. So as long as they can pull a weight at 1 meter per second, okay, the weight times the speed will give me the units in watts, okay, which would be the equivalent of 1 horsepower. So on average, a horse is good for about 750 watts, 746 watts exactly. Okay, that means if you put a horse on a treadmill attached to a generator, it could power 7.5 incandescent 100-watt light bulbs if everything was 100% efficient. Okay. Kind of devalues a horse a little bit, but that's what it could do.
So how come the UK use kilowatts?
Kilowatts is just thousands of watts, so it's thousands of joules per second, right? It's not changing. Like a watt is a joule per second, but anything with kilo in front of it is 1,000 times that. So it's still, so kilowatts, okay, is still a unit for power.
So how many horsepower is
1 kilowatt would be 1 point something. Yeah, 1.25 or something like that. 1.3, something like that. Okay. Everybody okay with that? Okay. This is kind of weird because horsepower is something that we really use often. And now, actually, with the metric system, the last time we went car shopping, they actually had the power rating in both horsepower and watts. If they ever go to just watts, I don't think I'll be able to go car shopping ever. Okay. It's like, oh, this car is good for 20,000 watts of power. I don't know if that's good or bad. If my kitchen blender is that powerful, I don't know. Okay, but watts is pretty meaningless for me if I'm trying to figure out how powerful a car is. Okay, so horsepower is probably something that will stick around. Okay, even when we're looking at things like an electric car. Okay, because even the Tesla is given a horsepower rating. I don't know what it is in watts, but whatever. It's an electric horse. Yes, it's an electric horse. All right, so simple power calculation. Again, you're not going to have to do a power calculation, but if we're looking at this problem here, I've got an 1,100 kilogram car that starts from rest. Okay, so I've got VI equals 0 meters per second. Okay, it's going to accelerate for 5 seconds. Okay, the acceleration will be 4.6 meters per second squared. I want to determine the average power generated by the net force accelerating the vehicle. All right, so we know that power is work divided by time, okay? And that work is force times distance, all right? Could I calculate the distance traveled with those 3 pieces of information? Okay, that's how these power problems would go, okay? Because the formula for power is so easy, there were usually lots of steps involved. So you had to calculate this, and that allowed you to calculate that, and then you could calculate power, okay? It wasn't really about understanding what power was. It was about how many formulas can you use without losing track of what you're doing. Okay, so it was probably a good idea that they took it out. Okay, well, we could do that here. Quickly calculate the distance traveled. Okay, so we would have 1/2 AT squared, so 0.5 times 4.6 times 25. Okay, so that would be our distance traveled, and then we could calculate the force, okay, by using the acceleration and the mass. Okay, so we would have 1,100 times 4.6 times our answer. Okay. And so there would be our power output. Okay, Sorry, got to divide that by time. I multiplied by time. Times distance. No, I got to divide by the time, just 5 seconds. Sorry. All right. So something like that. Okay. It's not. They're not like terribly difficult calculations, but again, you're not going to be asked to do it. So, okay. All right. Those are all the things we could have done. We're going to skip them. All right. We're going to look at this. Okay. And I think I have this in your workbook package, if I recall. I think it's in the workbook package. Hang on here. Okay, so go to Google Classroom and go to the class work thing here, okay, where the course materials is. Click on course materials and then view assignments so you can see what they actually are. You need to open the dynamics worksheet book. All right, and it'll be near the end. Okay, so it is starting on the bottom of page 9, okay, going on to pages 10 and 11. All right, so I want you guys to kind of read through that, and then there's a few questions to answer as you go, a few blanks to fill in, and see if you guys can handle those 3 questions there. All right, and then we'll walk through the whole thing together here in a little bit. Okay. Sorry. Explore the geopolitical consequences of having Superman turn a crank to provide an unlimited source of energy, and whether that was right or wrong. Because if we have Superman do that, then Superman essentially becomes a slave. All right, so there's this, it was some sort of explanation on that. But okay, so Yoda using the Force to run a similar generator. Okay, how much energy could he really supply? I don't know. This is sort of borders on the ridiculous, but this is where we're going with it. Okay, so Yoda's greatest display of raw power was the video clip we just saw, where he lifted Luke Skywalker's X-wing out of the swamp. Okay, moved it through the air and then set it down. All right, Luke Skywalker couldn't do it himself, okay, because he wasn't powerful enough or trained enough in the Force in order to harness his power and make it do the things he wanted. All right, so if we're going to calculate how much energy that took, because we need to know how much work Yoda did if we're going to calculate how powerful he is. Agreed? Right? Power is work divided by time, so we need to know how powerful Yoda is. All right, so if we want to calculate that, then we have to calculate the energy used to lift the X-wing. Okay, or the work done in lifting the X-wing. In order to calculate that, we're changing what kind of energy about it? It's potential energy. We're just lifting it. Okay, he lifted it at a constant speed. It didn't accelerate out of the swamp. He lifted it at a nice constant speed out of the swamp. All right, so that means we would take the object's mass, okay, times gravity times height. All right, so those are the things that we would have to have in order to do this. That means that we have to get measurements from the video clip, which, someone as nerdy as myself would probably have the time or take the time to do, just like this guy did. All right, so first thing is that there has never been a canon number given for the weight or mass of an X-wing, okay? And what I mean by canon is anything that now Disney says is true about Star Wars. Sad. Okay, but Disney has to say it's true, then it's canon. That means it's like the gospel according to Disney, okay, about Star Wars. Okay, that's kind of what it's saying. So we're just going to approximate. We're going to say that an X-wing, okay, whose length for some reason is in canon at 12.5 meters, okay, we can compare that to an actual aircraft that exists, okay, and that would be an F-22 that's longer, okay, so we're going to give an estimate for the X-wing to be about 12,000 pounds or so, okay, that means an X-wing is about 5,600 kilograms. That's what we're going to say it is. All right, then we need to know how fast it was rising. Okay, so what he did is he watched that scene over and over and over again and timed how long it took the landing strut to clear the water. Because in a previous scene in Star Wars Episode 4, there was a scene where a guy had to duck down and walk underneath the X-wing, meaning that the landing strut was about, I think he says 1.4 meters long, because the person had to bend about this much. So he's estimating the landing struts. See what I mean? This guy is almost as nerdy as me. Almost. Okay, he's still not on my level, but he's getting close. Okay, so 1.4 meters long. Okay, and then he timed how long it took for it to get out of the water. Okay, So he could, sorry, yeah, it ended up being, so it was 1.4 meters, and how long did it take? 3.5 seconds. All right, so he took the 1.4 meters distance divided by time, and he got the speed. What did the speed come out to be? 0.4 meters per second. Is that right? Okay, so we've got the speed. And the last thing we need to know is what's the strength of gravity on Dagobah, okay? And that's actually on this site that people have made called Wikipedia, okay? Chewbacca is a Wookiee, okay? So this is Wikipedia. I know, it's really nerdy. This is getting close to me now, like, yeah, okay? All right, so it informs us that the surface gravity on Dagobah is 0.9 G, which means it's about 90% of Earth's gravity, okay? So all we have to do is go 9.81 times 0.9, and we'll have the acceleration due to gravity on Dagobah, where Yoda lives. All right, so we got 8.829 as the gravity on Dagobah, so meters per second squared. All right, so now we can calculate, okay, how much work Yoda did in lifting the X-Wing, okay, and we can calculate the power by going force times velocity, okay? Everyone with me on that? So the force he exerts is 5,600 kilograms times 9.81. Or sorry, 8.829, sorry. 5,600 times 8, we'll just use answer, right? And then we do that times 0.4, right? So about 20 kilowatts worth of energy, worth of work, okay, done there, okay? So at current energy prices, Yoda would be worth about $2 an hour because he could generate 20 kilowatts of energy, which is nothing, okay? That's all that kind of showed. Right? Now, that's just one of the things that we saw in the Star Wars series about people using the Force. Okay, when the Emperor or any of the Sith people use their Sith lightning, okay, so they shoot electrical stuff out of their fingertips and they zap people. Okay, that is a huge amount of power. To make electricity arc through the air requires huge amounts of power. That's what essentially a Tesla coil would do. Okay, so we'd be looking at, you know, huge amounts of power for that. So what about Luke? He said, well, I examined the scene where he uses his force powers to yank the lightsaber out of the snow. That would have taken about 400 watts. So that, you know, there's at least a kind of a matter of scale here, where Yoda was clearly a lot more powerful than Luke, and he was 20 kilowatts. Okay, Luke was only 400 watts. Okay, so that was a fraction of Yoda's 19 kilowatts. Okay, so Yoda sounds like our best bet as an energy source, but okay, world energy consumption's pushing 2 terawatts. We're going to need a whole bunch of Yodas standing in front of these things going, rotate your wheel, charge my iPhone. Okay, we don't need that. Okay, it's just not going to be enough, right, for us to go ahead and laugh. I can do all of them. All right. So that's what we'd be looking at, okay, in terms of whether that would be useful or not. So the questions here, okay, if we're looking at a free body diagram of the X-Wing while it's still in the water, most obvious force acting on the X-Wing while it's still in the water would be gravity. Okay, so we would have, okay, other forces? Buoyancy, yeah. Now, we would have to assume buoyancy would be minimal, otherwise it wouldn't have sunk. Okay, so the spacecraft is probably full of water, okay, but there might be some air trapped in there, so there could be a little bit of buoyant force. What else? Well, once we get it moving through the water, then there wouldn't be much normal force left, but there could be a tiny bit. What's going to be the big thing when you try and move something through the water? Is it harder or easier than air? Harder, right? So there'd be friction, right? Water resistance that would be, okay, working against him. And then what's the other upward force? Yeah, Yoda. Okay, this is the other one. Okay, this is the one that makes the net force in an upward direction, or at least makes the net force 0, so it moves at a constant velocity out of the water. Okay. All right, so is the number you calculated a reasonable estimation of the work Yoda did in lifting the X-Wing? Well, we only took into account how many of those forces? 1. Okay, we only said he was working against gravity, but I mean, that thing could have been tangled on roots and vines and whatever else might have been at the bottom of that swamp. Okay, realistically, that number could have been quite a bit bigger if we considered all the other forces that were involved. Okay, number 3, assuming there's no air resistance, how much work did Yoda perform while the X-Wing moved horizontally? Okay, so he lifts it out of the water, and then he moves it horizontally through the air. How much work did he do during that part? Somebody whispered it. No. Yeah, no work at all. He didn't increase its height anymore, so he didn't change the potential energy at all, and he moved it at a constant speed through the air, so he didn't change its kinetic energy at all. So the part where it's moving horizontally required no work at all. Okay? It just moved along and no energy changed, right? Then when he lowered it, he basically just allowed gravity to bring it back down. Okay? All right, that sort of makes sense? Okay. All right, so that's all we really need to know about power. Okay, is that stuff there. All right, so what I want to go back to today is some stuff about conservation, law of conservation of energy. All right, so I'm just going to put a question, I'm going to make one up here that I want you guys to try. That's kind of a work energy theorem / conservation of energy type of problem. Okay. Oh, I guess I better give you the mass. All right, give that one a try. Okay, so looking at one like this, okay, like I say, there's 2 methods to solving this one, right? And the first method is using the work energy theorem, right? So we have a 50 kilogram crate, sorry, 500 kilogram crate, okay, being pushed or pulled upwards with, we said 6,000 newtons, right? Okay, which is way more than we need on a frictionless ramp for this thing, okay? But I was picking numbers out of my head. That's what happens when I do that. So we got 6,000 newtons worth there. We've got a 15-degree angle, and we know that this is going to cause a change in both potential and kinetic energies. Agreed? All right. Can I calculate how much work is done in total right now? Yes, I can just go that force, the applied force, times the distance. What I need to remember is that that means that's the change in both the potential and the kinetic energy for this particular case. Everyone all right with that? Okay. So I'm going to calculate the total amount of work done right now. That's going to be force times distance, 6,000 times the 20-meter length of this ramp. Okay, that's going to be 120,000 joules. All right. If I'm going to calculate the speed at the top of the ramp, I need to know the object's what at the top of the ramp? Okay, yes, I do need to know the height, but even more importantly than that, if I'm going to calculate its kinetic energy, I need to know its velocity, right? I need to know its speed. Now, the only way for me to get that is to get the potential energy at the top and do what with it and this number? Subtract them. Okay, if I subtract from the total work I do, how much of that work changed potential energy, I'll know how much I changed the kinetic energy by. Because at the bottom, it didn't have any energy at all. All right, so whatever that change is that's left is the change in the kinetic. Well, if I'm going to find the change in the potential energy, I need to know the height of the ramp. Can I calculate that right now? Yeah, I can calculate the height of the ramp because I know how long the ramp is and I know the angle at which it's tilted. All right, so the height is going to be the sine of 15 degrees times 20 meters, and that comes out to like 5.17 or something like that. Okay, so we got sine of 15 times 20. All right, so 5.176 meters. All right, so now I know the total work and I can calculate how much of that work changed the potential energy. All right, so I'm going to go that EK equals the work minus the potential energy. Everyone okay with that? Because the work is really the mechanical energy at the top of the ramp. Agreed? It didn't have any energy at the bottom, so all the work I did became mechanical energy, and really all I'm doing is calculating EK. All right, I'm gonna kind of skip calculating that by itself and do this instead. 1/2 mv squared equals 120,000 joules minus m times g times h, okay? That's also true, agreed? Basically the same thing. So if I want to calculate V, I'm just going to divide both sides by half of m and square root. Right? That'll give me V. So when I do that, I'm going to have 120,000 minus 500 times 9.81 times 5.176 divided by half times 500. Okay? That'll tell me how fast I'm going at the top. Everyone follow what I did there? Okay, so just work energy theorem. So we'll have our oh, 250. All right, so I'm getting that it's moving at 19.4 or 19, actually 19 point. I only have two significant figures, so it's just 19 meters per second at the top of the ramp. Everybody okay with that? Okay, so that's method one. Okay, that's what we got, 19 meters per second. Okay, the second method involves using the forces instead. Okay, now which force changes the kinetic energy? Applied or net? The net force. Okay, remember, this is my applied force. It changes the mechanical energy. Okay, the part that's left over after having changed the potential is the net force, and that's what changes the kinetic energy. So I can find the kinetic energy by calculating net force times distance. Okay, because the work done by the net force changes the kinetic energy. All right, because the net force causes the object to do what? To accelerate. Okay, so if we're looking at that, I've got to calculate net force. All right, so that means I got to go back to here and I've got to draw in some of my other forces. All right, I won't need to know Fn. This side here will be 4,905 newtons, and this side here is F parallel. So I'll need to calculate it doing what we always do with our inclined planes. So I'll take my I'll go sine of 15 times the force of gravity, 4905. There's my F parallel. Everyone with me so far? Okay, so now I've got F parallel, and if I want to find the net force, it's going to be 6,000, the force up, minus this, the force down. Everyone all right with my logic there? Right, because those are the only two forces acting. So if I go 6,000, okay, minus my F parallel, here's my net force. How much distance does my net force act over? 20 meters. All right, so I'm going to take this number. I'm going back to this calculation now. Okay, EK equals F net times D. Right, I've got F net. I know D is 20 meters. So now I can calculate the speed. Right, because this is going to be 1/2 mv squared equals F net times D, and I'm just going to divide both sides by half of m and square root. So we'll have our 4,730 times 20 meters divided by 250, half the mass, okay, square root. Okay, divided by 250, square root that. Exactly the same number, okay. Speed at the top, regardless of which way I calculate it, comes out to 19 meters per second. I could, but oh, I see what you're saying. Find acceleration, use the distance, VI being 0. Yes, boy, that's a lot more work though. Yeah, okay, because that's every step I've already done, plus then I've got to do an acceleration calculation after that. So you could, but if we're trying to do this efficiently, method 1 is the more efficient choice. This method 2 is not far behind on this one just because of the givens I gave you, okay? But method 1 is still the most efficient. Got it. Because the force and the distance were parallel, right? The force was up the ramp and we were moving up the ramp, right? So I didn't have to put in the cos of theta part there. Yep. All right. Ringing a bell? Making some sense? All right. We're going to leave it at that for today. Okay, you will have a quiz tomorrow on conservation of energy. I'll post it later on today, right? And tomorrow we will do our unit exam review. So maybe have a look at some stuff from this unit and see if there's any questions you're going to want to ask tomorrow in regards to what might be on the test.